Hello, my name is Chance Lee. I will start presenting Termproject 4. Full cycle is a term used when the price of memory semiconductors rises as demand increases and supply can keep up, and refers to an ultra long-term boom in the semiconductor memory market. If you look at the graph on the left, memory price rise and fall every 3 years. The super cycle is said to have occurred when the price of memory peaks again. This is the first chicken game. Due to the low price offensive of three Japanese companies, NEC, Toshiba, and Hitachi, the price of DRAM fell from $3 to $0.3. At this time, Samsung Electronics was recording a deficit of $200 million per year. In the end, the first game of chicken ended with Intel's surrender and the Japanese company's victory. Excellent Technology Japan produced a $1.25 per sheet with a yield of 80%, and the United States produced $2 per sheet with a yield of 50%, so Japan wins. This is the second chicken game. A second chicken game breaks out the Taiwanese DRAM company's race to increase production. Due to price reduction competition and IMF, the price of DDR2 RAM has dropped to $0.5. In this competition, German's Kimonda goes bankrupt. At this time, Samsung Electronics survived by making two big decisions: adopting stack technology and changing wafer size from 150mm to 200mm wafers. This is the third chicken game. Japan and Taiwan are working together to increase the supply of DRAM by investing in semiconductor production facility and equipment. 1 GB DRAM fell below $1, and the company faced to loss again. Eventually, Japan's Elpida went bankrupt and was acquired by Micron. Samsung Electronics and Hynix survived by focusing on selling products that the market wanted at a low price, shortening production times, and improving yield. This is a super cycle prediction. In the fall of 2022, SK Hynix and Micron reduced their facility investment by nearly half, causing semiconductor supply to bottom out. But I don't think the semiconductor cycle will go down because of this. 40% DRAM demand from server. There is steady demand because big tech companies face problems when their server break down. Additionally, as technologies such as ChatGPT, Metaverse, self-driving car level 3, demand for semiconductors will increase. In particular, self-driving car level 3 must be equipped with at least 15 gigabytes of DRAM. I believe that the super cycle will return in 2025 when level 3 vehicles are expected to be commercialized. This is Nature paper that plans to explain the semiconductor structure. The impact factor is 69.054. The title and author as follows, and the publication year is 2011. The reason I chose this paper is because it explains well through graph the problems that arise as the size of MOSFET becomes smaller and the degree of integration increases. A planar path is the basic structure of MOSFET. Source on the left, drain on the right. It consists of the gate between both sides and substrate below. If it is formed on p-type substrate, as shown in figure 1a, it is called an N-channel MOSFET. In the case of N-channel, the source and drain are doped with N-type electrons. The electric field formed by applying a voltage to the gate forms a channel between the source and drain. Electron pass from the source to drain through the channel, creating a flow of current. The core of the MOSFET's operation is to control the amount of current flowing between the drain and source by controlling the voltage at the gate. The graph in figure 3 on the right shows the transistor gate length and density over time. The yellow circle is MOSFET gate length, and you can see that the gate length gets shorter over time. The shape represents the number of transistors per square millimeter for the four company list. In 1970, there were 200, but in 2015, you can see the number of increasing to over 1 million. As you can see in figure 1b, there is a depletion layer below the source and drain. As the size of transistors gets smaller, the channel lengths get shorter and problems arise. This is called the short channel effect. One of the phenomena that occur due to this is called DLBL, drain induced barrier lowering. As the channel becomes shorter and reverse bias is applied between the drain and the body, the depletion layer area gradually widens in the direction of the body, invading the channel and lower the potential barrier between the source and the body. Due to this DLBL, gate driving power is reduced. At this time, when the two depletion layers touch each other, a leakage current is generated through the depletion layer touching from the source to drain, even if no gate voltage is applied. The x-axis of the graph in Figure A is the channel length, and the y-axis is measured DLBL. Looking at the graph, you can see that the longer the channel, the smaller the DLBL. If the length of the channel is short, you can see that the DLBL increases. Existing planar FET only control the channel current on one side. So as the size gets smaller, the area of the channel that the gate can control narrows, making fine control difficult. Therefore, the next structure that appeared was a FinFET structure. In the case of FinFET, as shown in Figure 5a, the gate surrounded a channel, allowing the flow of control to be controlled on three sides, resulting in better control characteristics. Since the channels are formed vertically, the size of a semiconductor is further reduced. And as the number of channels increase, more current can flow, reducing leakage current or short channel effect. However, problem arises with FinFET as the integration level increases. The distance between fins become closer, and if thin fins are stacked high, they will bend sideways or collapse. As the FinFET has limitations beyond 4 nanoprocess, GAE FET was developed to compensate for this. As shown in the Figure 5e, GAE FET has a gate that surrounded the channel on four sides, which increased the surface area and improved current control characteristics. The advantage of GAE is that even if the number of channels increased by stacking channels, the bottom area occupied by the pad does not change, and current control characteristics can be improved. This is Nature Electronics paper reference to explain next generation semiconductors. The impact factor is 33.225 and title and also as the followers, and the publication year is 2019. The reason for selecting this paper was that it explained well through numerical graphics and the characteristics of ternary transistors, which are different from existing binary transistors, and the advantage that can be obtained by using them. The type of next generation semiconductor that I think is a semiconductor that uses the ternary method as shown in Figure 1a. First, the ternary CMOS structure in Figure 1a. It is a combination of two inverted elements, N-channel MOSFET and P-channel MOSFET. Unlike conventional MOSFETs, a bridge is placed between the source and drain, so current flow is without voltage. This is called the tunneling effect. The tunneling effect changes the characteristic of the switch. I will explain by looking at the graph in Figure 1d. The upper two lines on the graph correspond to normal MOSFET, and the lower two lines correspond to ternary CMOS. Looking at the two curves below, you can see that the current does not rise even as the gate voltage increased, and only increased when it rises above a certain voltage. You can see this characteristic by looking at the graph on the right. And unlike regular CMOS, you can see that signal is divided into three steps, such as 0, 1/2, and 1. You can use this to create a ternary switch. I will explain the advantage. Using the binary method, assuming there is n CMOS, you can store 2 power of n signals, while using the ternary method, you can store 3 to power of n of signals. For example, 2 binary CMOS can produce 4 signals, and 2 ternary CMOS can produce 9 signals. If the number of CMOS increased to several million, the number of signals that can be generated varies exponentially. You can see that ternary CMOS require much less area, cost, and power when sending out the same number of signals. Therefore, I believe that ternary CMOS technology is that can gain significant advantage in the semiconductor market, where the level of integration determines the outcome. This is the reference that I used. Thank you for watching.